But my background is I have a bachelor's in physics and mathematics. I did that in Minnesota. Then I got a PhD in material science. And kind of an overview of the talk is I'll kind of go through a kind of a focus of the research, kind of the motivation of the group, the rationale for what we do. Then coupled with this, I'll have kind of three main topics, but I'll slide forward. We'll talk about our use of droplets and liquids, right? And kind of the physics of how droplets and liquids wet, wick, and dewet. And then related to this, there's something called Hemiwicking. So if you start structuring surfaces, the fluids start moving on the surface in a well-defined way. And there's heat pipes, and I'll show an example of that in computers and whatnot. But then we're interested in soft matter because we're gonna start going to flexible electronics. And then there's also this whole idea of, can we start chemically functionalizing the surfaces, and how does that influence play a role? Then kind of slide 6, the second topic will be on jet spray cooling, kind of talk about some of the metrologies we use, some of the attempts we've had with using quantum dots as temperature sensors. And then slide 7 will be kind of my view on where I really want to go in the future, applying metamaterials. And this is kind of the multidisciplinary way of doing things, where you use a metamaterial to not only actively tune the optical properties, but also the thermal and the fluid. And so potentially we'll see if this can be done. It's hard enough to do active tuning of optical, let alone adding these, but potentially metamaterials can do that. So kind of a research focus, motivation. So if I put it in 3 bullet points, it would be, solutions for extreme environments. And so what is an extreme environment? High temperature fluctuations, high temperature, high magnetic fields, high pressures, but also in terms of that extreme heat flux kind of extreme environment, then there's transient loads. And so Alexander's talk right before was very fitting, because he talked about in power systems, there's this dynamic aspect that is a challenge. And also it's the frequency, changes in frequency and changes in amplitude. Well, the same thing happens in thermal management. So we're dealing with high heat flux systems, and there's a lot of transients in the timescales. And so the same applies. And so if we look at, he's looking at Alex was giving a talk on large power systems. And here I'm more interested, is interfacial transport laboratory. So we're looking at the micro and nano and interfacial effects. And so here I give an example of, this is a horny devil lizard. It sets its belly on the desert floor, and then it wicks up water to its mouth. Icing on engine blades. Okay, if you shoot a laser at a pilot, you want to suddenly darken the lenses, so transient, right, absorption. Heat pipes and cell phones. And then there's this kind of overview of, cooling of a 3D stack of quantum cascade lasers. So in terms of wetting, wicking, and dewetting, I'll just pose this question. How fast can you wet a surface? What are the fundamental limits? And then if you know that, now can you control the direction of wetting? So here's an example where you put pillars on a surface and it wets this way. And here's an example where we just put water on water. And then here's an example of where we have a water droplet, and keep in mind the shaded regions are kind of mirror reflections. This is on a really hot surface, so the water really doesn't wet. It just sits on top and does what I call schizophrenic solid liquid handshaking. So for all of these, what are the physical limits? Surface changes in surface energy, changes in surface chemistry. Is it chemical kinetics or is it thermodynamics? So I'll just leave that as a question. So in terms of applying these structures and how fast you can wet a surface, we can look at microfarad surfaces, and then we can chemically functionalize them, and then we can make these surfaces in many ways. We can do dip coating, drop casting. We use a lot in our lab this micro machining, basically just a drill bit put a bunch of holes in plastic, use PDMS processing, cure it, or we can use advanced techniques like the nanoscribe at AFRL and Oak Ridge National Lab, and we can make these anisotropic pillars. And then since we're on soft material, then we can look at the modulus. How stiff is this soft matter? And here's an example of the pillars bending over after they've wicked. And here's an example of the wicking front as the water wicks up as a function of time. So my student's been working with a graduate student in Karen's group in chemistry at UCF, and we've been trying to do this photoacid, right? So if you shine light on a photoacid coating, can we change the surface energy? And you know, I have to say, Karen and her student have been, and my student have been working really hard, but this is not a simple chemical thermal engineering problem. So a lot of work needs to be done. Kind of the second topic is related to, since we have these transients, we have to understand how much does the temperature change? So to cool things, there's such thing as spray cooling, so we can put a spray on a hot surface, and then we have all these advanced diagnostics, so we can use IR imaging and high-speed imaging, and we can have pulse jets or pulse sprays. And then this induction, this multi-spray approach is kind of a current collaboration. We'll see, I sent an abstract, so we'll see if it gets finally approved for NSF GOLI. But this is related to pulse spray cooling for various applications. And I'm working with Yunjin Xu. He's done some preliminary work with controls theory, and then Jay Ambrose at Lockheed Martin, California. And then here's just an example of what we can measure, and then our attempts on theory. I say theory, but it's not theory because it's just what we've come up with. So I think this is a good highlight. I really, would like some theoretical help on predicting these things. Just, I think Alexander mentioned, what is the solution to this differential equation, right? So there's similar aspects here, and you go to transients. We need some theory on predicting these rates of heat transfer. And then the last final topic, I don't know how much time I have. I forgot to start my timer. Sabith, could you tell me how much?
Yeah, you have 5 minutes.
Oh, I have 5 minutes. Good. So
5 minutes with Q&A.
Okay, so 3 minutes. Or 2 minutes. So this is the kind of the direction I want to, this is where I see the future of my group. So I talked about chemical functionalization. I talked about physical changing of surfaces. So now let's consider that we put pillars on a surface, but now we coat all of these pillars with a metamaterial. And so these are anisotropic pillars. So I should point out, because of the physical geometry, it's not isotropic. It wicks faster in this direction than this direction. Okay, so take those pillars, and now let's put a metamaterial on top of it. Can we start tuning not only the optical properties, but the thermal and the fluid? This is some preliminary work where we take this nonpolar fluid, we have a metamaterial on top of Kapton, so a soft matter, and then we strain it. So we pull the Kapton. So we start changing the electron density or the charge carrier density, and we start softening the lattice as we strain it. And how does that influence the frequency dependent dielectric constant? And so you can see here that when we go down and we strain it enough, suddenly it becomes super wetting. And then here's a lot of calculation. Here's some data on contact angles. And here are some calculations on how we can predict surface energy. And there's a lot of details here, but really I would like some theoretical help on how we can predict how strain influences the real and imaginary part of the dielectric constant as a function of frequency. And collaboration with this at AFRL, and then John Jones, where we've made things like this. And then this is in our work. This is just something that you can read at physics.org. And here's an example where you take this engineered multi-layer structure and suddenly you can have a negative index of refraction. So short-term proposals help with theory, simulations, modeling, chemistry, sample fabrication, and of course, you know, I need help with new and better ideas, right? And the midterm is the same thing, basically, and then long term, this high temperature, robust, soft metamaterial systems with tunable, multifunctional abilities. And then, you know, just some general acknowledgements, you know, thanks to the Lord, you know, for the, you know, just in general that I'm, you know, I'm safe, especially in today's time. And then, you know, passing current funding, and then with the research team. And then here's a bunch of undergraduate and graduate students. And thank you.
Um,